let's talk about friction. Before I get into the equations, let's just talk intuitively right now. So let's imagine you're trying to push a very heavy refrigerator across the floor. I'm not very strong. So at first, no matter how hard I push, the refrigerator doesn't move, right? So why is it not moving when I'm pushing on the refrigerator? What force is opposing my force?
Static friction.
Yes. So the refrigerator is not moving because the floor is exerting an equal and opposite static friction force on the refrigerator.
Static just means not moving.
Exactly. So static friction is the force that resists the start of sliding motion between two surfaces that are in contact. The special thing about static friction is that it adjusts itself. So if you push a little, static friction pushes back with the same amount. If you push harder, static friction increases to match you. But there's a limit. So the largest possible static friction force, that's the maximum static friction, is mu s times n. So mu s is the coefficient of static friction. So it's a unitless number and it depends on the materials. For example, glass on glass is going to have a different coefficient of static friction than wood on wood, for example.
Or wood on glass.
Or wood on glass, yeah,
Or concrete on glass.
exactly. So N is just the normal force, just like we saw. All right. So that's static friction. So once your push force is greater than Fs max, the refrigerator is going to begin to slide. So now the situation changes. So once the object is sliding, static friction no longer applies. So instead, the force that resists the motion is kinetic friction. So kinetic friction is the force that opposes the motion of two surfaces that are in contact and are sliding over each other. So again, mu k is the coefficient of kinetic friction. It also depends on the materials. It's also unitless. And it's usually smaller than mu s because it usually takes more force to get an object moving than to keep it moving, right? And n is the normal force, just like I used the whole video. And I'm using lowercase f for friction, for frictional forces, and then capital F is just for forces in general. All right, let's do example 2 now. A small crate rests at one end of a wooden plank that is 2.5 meters long. The coefficients of static and kinetic friction between the crate and the plank are mu s equals 0.550 and mu k equals 0.350 respectively. The end of the plank where the crate is located is slowly lifted until the plank makes an angle theta with the horizontal, at which point the crate begins to slide. If the angle is maintained at theta as the crate moves, what is the speed of the crate when it reaches the bottom of the plank? So,
This is a juicy one.
very juicy problem, lots of words. So, let's draw a picture. So, I'm going to draw the plank. I'll make it brown because it's a plank. And I'll just draw invisible legs to make it a triangle. And we have a small crate at one end of the wooden plank. So let me draw like a box.
Shouldn't it start right at the top?
Maybe I'm drawing it when it's sliding, Doesn't really matter. What forces are acting on the crate?
Gravity.
Yeah. So that's straight downward. And I can say mg now because
Because you wizened up, that's why.
yeah, sure. We don't know M though, but I'll just write mg for now. It's okay. But we also have normal force because the ramp is exerting a force on the crate. So like this. And what other force do we have? There's one more.
Friction.
Yes. Because it says coefficient of static and kinetic friction between the crate and the plank. And what direction is the friction going to be in? Looking at the diagram, like tell me where the arrow is going to point for friction. It's going to be in this direction because the box is accelerating down the ramp, right? So this is the acceleration, call it A. The box is moving down the ramp in this direction, so friction is gonna oppose that motion. It's gonna be in the opposite direction. It's gonna be up the ramp. These are the 3 forces on the box, and we also have that the plank makes an angle theta with the horizontal eventually. I guess one other thing I'll label is that it says the plank is 2.5 meters long, so I'll call that D for distance. So, what coordinate system are you guys thinking? Are we gonna do the standard X and Y?
Yes, we are going to do the standard X and Y. It's just the standard X and Y will be oriented along the ramp.
Interesting. So you're thinking parallel to the ramp and perpendicular to the ramp?
Yeah, but in a superior notation than that, yes.
And why is that coordinate system gonna make our lives easier? Like I said in the last problem, it's a good idea to align one of the axes with the acceleration vector. So it's a good idea to do parallel and perpendicular for this one because the only vector you'd have to break into components is the weight vector. Everything else is going to be parallel perpendicular. Okay, so let's do the problem now. We're trying to find the speed of the crate when it reaches the bottom of the plank. You're probably thinking speed. I'm working with F equals ma, so I have a bunch of forces equals mass times acceleration. Where is speed going to show up? Well, first we need to find acceleration, and then we can use the kinematic equations to find speed. You can use one of the kinematic equations to relate a and v. So before we get into finding speed, let's find acceleration. So to find acceleration, we need to look at the parallel direction because A is 100% in the parallel direction. There's no acceleration in the perpendicular direction. So let's look at the sum of the forces in the parallel direction. So sum of the forces in the parallel direction equals ma in the parallel direction. So let me break this weight vector up into its parallel and perpendicular components. So here's the perpendicular component, and here's the parallel component. So the forces in the parallel direction, we have mg parallel, that's one of them, minus the frictional force. So which friction is it going to be? Is it going to be static or kinetic friction?
Hasn't started moving yet, right?
Well, the thing is, if it hasn't started moving, then the acceleration would be 0. We're trying to find acceleration, so let's say that it's moving right now. So we'll go with kinetic friction. So I'm going to say F sub k. I'm subtracting it because it's in the opposite of the positive parallel direction. All right, and that equals m times a parallel. A in the parallel direction is just a because it's 100% in the parallel direction. So I have mg parallel here, and let me write it in terms of mg. So I need to do some angle stuff again. So I need to figure out, is this theta? Is this theta? So we can do the same thing as last time as example one. Remember, this is a right angle, this is a right angle. This angle in this triangle is the same as that angle in the big triangle, right? It's congruent to itself. So that means this third angle here has to be theta, right? This is theta, which means this has to be theta because alternate interior angles, right? Since these two lines are parallel, these two angles are going to be congruent. Okay, so this is theta right here. Since mg parallel is opposite that angle, I can say mg parallel is mg sine theta. And then the kinetic friction, we have the formula here. It's mu k times n. Okay. So we're trying to find A because we need to find A first, and then we can find the speed. The thing is, we don't know n, and we don't know m.
Lacking n, that can be easily remedied by using another equation in the perpendicular direction.
Yes, so let's try to find n. So what I'm going to do is let's look at the perpendicular direction because n is in the perpendicular direction. Here, I can move this down. And I'll do the forces in the perpendicular direction now to find n. In the perpendicular direction, we have n minus mg perpendicular. So n minus mg perpendicular. And what is a in the perpendicular direction?
The answer to your query is that the acceleration would be zero in the perpendicular direction.
Exactly, because
It's not levitating off the ramp, or it's not falling inside the ramp either. So it's got to be zero.
that's correct, because a is 100% in the parallel direction. So a perpendicular is 0. So that means m times 0 is 0. Okay, so that means n, if I add mg perpendicular to both sides, you're just going to get n equals mg perpendicular. And mg perpendicular, it's adjacent to theta, so it's mg cosine theta. We don't even need m because
Well, we're
what I
just going to plug in n into the F parallel equation. So you have
yeah,
mg sine theta minus mu k mg cosine theta equals ma, and then the m's all cancel out.
exactly. So that's good. We don't have to worry about m anymore. So I can divide both sides by m, so it'll all cancel, and you'll get a equals g sine theta minus mu k g cosine theta. We don't know theta. That's another thing. We did parallel and perpendicular while the crate is moving, but we can also do it when it's not moving, just before it slides. So that's where the static friction comes in. So we can use that to find theta. So since we're working with friction, let's do the parallel direction. But now this is just when the crate begins to slide. This is before it started moving. Before it starts moving, we have the sum of the forces in the parallel direction are mg parallel minus F, specifically Fs max, right? Because we're looking at the maximum static friction when it just begins to slide. That's what the problem says right here. Slowly lift it until the plank makes an angle theta with the horizontal, at which point the crate begins to slide. So we're looking at that moment. And when it just begins to slide, it's not really moving yet, so A parallel is 0. So this equals 0. Okay, so MG parallel is opposite the angle theta, so it's MG sine theta. And Fs max, if you look at the formulas here, that's just mu s times n. And we know n, we did that earlier. N is mg cosine theta. So I'm going to substitute that here. So it's going to be mu s times mg cosine theta.
Mg cancels out.
Yes, that's great. So the mg's cancel. You can divide both sides by mg. And you're left with sine theta minus mu s cosine theta equals 0. So we can find theta because we have mu s. It's given in the problem. These are the coefficients of static and kinetic friction. So to solve for theta, I'm going to add mu s cosine theta to both sides. And I'm going to divide by cosine theta. So I get mu s is sine over cosine, which is tangent theta.
And to isolate theta, we just slap an arctan on that.
Yeah, so theta is just inverse tangent of mu s. So great, we have theta now. So what I'm going to do is I'm going to plug that into the acceleration equation because we're trying to find acceleration, which we're going to use to find speed. I see both terms have g in it, so I can factor out the g, and now I can replace theta with inverse tangent of mu s. So sine of inverse tangent of mu s minus mu k, and I factored out the g, cosine of inverse tangent of mu s.
It's a bit of a chunky expression.
Yes.
Yeah, it's good practice to put everything in variable form until the last minute.
And again, we're trying to find speed of the crate when it reaches the bottom of the plank. So the thing that connects acceleration and speed is the kinematic equation. So I attach that over here. We don't have any information on time. So automatically, we're not going to use these three equations. So the only equation left for us to use is this one.
It's
Because
a good equation.
yep, because we have initial velocity. It's zero because it starts at rest. We just found acceleration. We know the change in position. It's d, what I said earlier, the 2.5 meters. So we can find the final speed. So let me write that down. The final v in the parallel direction squared equals the initial v in the parallel direction squared plus 2a times the displacement, which is d. So, like I said, the problem says that the small crate, it starts at rest. So this right here is 0. So to find the final speed, I just have to take the square root of both sides. So the parallel is the square root of 2AD. So we have A, this is A, and I'm going to put a 2D in front of that, and I'm going to take the square root of this whole thing.
Hopefully that all works out to meters per second, which I think it will.
Yeah, this is all unitless. This is meters per second squared. This is times meters. So it's meters squared over second squared, and we're taking the square root of that, so it's meters per second. So the units at least work out.
Always do that when you have time on the exam.
Yes. I took this to the extreme and I didn't use any numbers. I just kept going with variables. Most people would actually find theta and plug it in. I don't think a lot of people keep it as inverse tangent the whole time, but I'm
I
just
would do that. It makes it easier for the TAs to grade.
yeah, but this is the speed at the bottom of the plank, all variable style. I didn't put anything in my calculator yet. But now it's time to do that. So let me plug in all the stuff we know.
How many decimal places you want for this?
Well, let's look at the problem. That depends on how many sig figs I gave in the problem. So it looks like 3, because everything has 3 sig figs in this problem. So V parallel is about 2.93 meters per second.
I think I've seen enough inclined planes for today.
Yes, and that's with parallel and perpendicular coordinate system. This would have been way worse if it was X and Y standard coordinate system.